Hello and welcome to this video. In this video we're going to be going through the topic of momentum. Now we would have already met momentum before at GCSE. We should know that anything that moves has momentum. That's kind of the idea of momentum. Now we should also know an equation for momentum, and we know that momentum, which we're now going to note as a P. You might have not noted this as a P before, but since we can't note it as an M, because mass is already M, we just choose P, because why not, you know? So the momentum is equal to the mass multiplied by the velocity which something moves at. Okay, this is your equation for momentum. Okay, so this is mass, and we always measure mass in kilograms because we're at SI units, and this is velocity, which we always measure in meters per second because of our SI units, which means momentum is measured in kilograms meters per second. So I'm just multiplying these two units together to get the units of momentum. Now this equation we should be able to apply pretty easily. If I say that I have a ball of mass 2 kilograms traveling in this direction at 5 meters per second, we should just be able to see that P is equal to the mass times the velocity, so P is 10 kilograms meters per second. Okay, that is fairly straightforward. So the first thing we have to make sure is that we understand that because velocity is a vector, notice how I drew this arrow for a direction, momentum is also a vector. Okay, so it does matter what direction it's moving in. So like before in all the forces questions, we had to define a direction to be positive. I have defined this direction to be positive. If I were to then take the same example and say that this 2 kilogram mass is actually traveling in this direction with 5 meters per second, if I define this direction to be the positive, then the momentum is going to be negative 10 kilograms meters per second, because the velocity is technically minus 5 because it's going in the negative direction this way. Okay, so this equation should be fairly straightforward. Now the thing that we have to also make sure that we know is that momentum always has to be conserved. Like charge or energy or anything like that, momentum is also a quantity that has to have conservation. So the conservation of momentum means that if I were to take a collision, so I can have collisions between particles or between a car and a wall, or two cars or two balls or anything like that, any collision, momentum before the collision has to be equal to the momentum after the collision. So it's the sum of all momentums, before a collision must be equal to the sum of all momentum after a collision. And there is a caveat to this, okay? There's an extra line that people often miss, and that is the fact that this has to be without external forces, as long as there are no external forces. So this line here is a very important line that we'll get back to in a second. For now, we need to look at what types of collisions can we actually have. Now, there are two types of collisions. You might have already met these at GCSE. We have elastic and inelastic collisions. Now, in all collisions, momentum has to be conserved. So in both of these, we conserve momentum. Okay, as long as there are no external forces applied. But in elastic collisions, we also conserve kinetic energy. Okay, kinetic energy is also conserved, whereas in inelastic collisions, we'll lose some kinetic energy. So an elastic collision, if you wanted to recognize it just by looking at the situation, you can guess whether it's going to be elastic or inelastic based on the idea that if things bounce off each other, or if something bounces, it tends to be an elastic collision. So an elastic collision tends to be bounce, whereas inelastic tends to be when two objects join together, right? So for example, if I had a wall and a ball bounced off a wall and came straight back, this could be an example of an elastic collision. And if I were to throw a ball at the wall and instead of bouncing off, it just slid down the wall, almost like a beanbag. If you throw it at the wall, it just gets stopped and then falls straight to the floor. That would be an inelastic collision. Now, I will say this is not a perfect method. Okay, it's never going to be completely accurate. It's a good estimate to give you a rough idea of whether it's going to be elastic or inelastic. But if you wanted to fully prove that something is elastic or inelastic, you need to look at the kinetic energy. Okay, so not a foolproof method. Yeah, there will be situations where you can have a decrease in kinetic energy even with a bounce. Okay, it entirely depends on the material that you have. Okay, so now let's investigate what this conservation of momentum tells us if we do have an external force. Okay, so if we were to assume that conservation of momentum is true for everything, right, and if we have momentum, it must always be conserved in every collision. That means if I start a car moving, so this is a very rough idea of a car, right? If I start this, it has some mass and it's moving with some velocity. If this has momentum, the only way, if we miss out this external forces kind of thing, the only way to reduce this momentum is to have it collide with something. And when it collides with something, that thing must then continue to move with the same momentum, which means we'd never be able to stop a car, right? So we'd never be able to hit the brakes, because what we'd have is just another car that we'd crash into. And then this will then, assuming they have the same mass, when this collides with that, this one is now going to become stationary and this one will drive away with the same velocity. Okay, that would be a conservation of momentum. However, we obviously know we can stop a car, we can hit the brakes, right? And that brake is the external force that we're applying, okay? And the brakes are causing a change in momentum. So now, if we hit the brakes, it means that we're applying some force. Now we have to go back to forces for a second, and we have to then say force must be equal to ma, as always, okay? But a, we can also say, is equal to the change in velocity divided by the change in time. Okay, so now if I substitute a into here, I can say that F must be equal to m times delta v divided by delta t, which I can then simplify to say that F equals the change in mv, now we know mv is momentum, divided by the change in time, and that is your expression for the force. Okay, so the force that acts on something is equal to the change in momentum divided by the time. Okay, so what this time means is how long does it take for that change in momentum to occur. So for example, if we continue with this car idea, the time it takes in order to come to a stop will be the time when the change in momentum will be the momentum it started with to 0. Okay, so this is your equation that you'll see on the formula sheet, and this will allow you to calculate pretty much anything to do with forces and momentum. Okay, so from here we can then rearrange it slightly for just a second equation, and so we can introduce this idea of impulse. Now impulse literally just means the change in momentum, so it's not really a fancy new term, it's just a different way. So saying change in momentum is really long, so we just say impulse instead. So impulse is the change of momentum. Okay, Now, the change in momentum we already have a formula for, and that means that F is equal to the change in momentum divided by the change in time, which means I can therefore rearrange it so that F times delta T is equal to the change in momentum. And this is the formula sheet formula that you'll get. Okay. So this is everything that you need to know about forces and momentum and everything that's coming up to this point. I'm going to do a very quick example to run you through how we would approach these calculations. I'll do one without external forces and then one with external forces so that you can see the difference. So let's now call this one example 1. Okay, example 1. I have 2 balls, okay, and this ball weighs 1 kilogram, okay, and this ball weighs 2 kilograms. Now, this ball is moving towards this ball with a speed, let's go with 3 meters per second, okay. It then collides with the ball, so this is what happens before the collision. Then after the collision, it collides with the ball, and these 2 balls stick together and they both move at some velocity v meters per second. Okay, now I'm going to define this direction to be positive, and the question will ask you, what is v? So what is the velocity that they both travel at? So what we need to do is say the momentum before the collision must be the same as the momentum after the collision. So I'm going to note that as the total momentum before, so I'm going to note that as P before, momentum before, is just down to this object here, okay? Because the velocity of the 2 kilogram ball is 0, so its momentum is 0, okay? So the momentum of the 1 kilogram ball is 1 times 3, which is 3 kilograms meters per second. Okay, now that also means that momentum after must be equal to 3 kilogram meters per second, because they have to be conserved. We have to make sure this is true because we have no external forces applied. Now we know the expression for the momentum after is going to be the total mass that's moving multiplied by the velocity they move at. So P after is the total mass. Now that they've joined together, you can actually just sum their masses together. So they join, so this is 3 times V must be equal to 3 kilograms meters per second, and so we can conclude from that V must be equal to 1 meters per second. Okay, so I purposely chosen very easy numbers for this to make it a very simple, straightforward calculation, and so this would be an example. Now, the things that I would say be careful of is when things move in opposite directions. That's always something you need to be careful of. So careful of vectors. And apart from that, these should be fairly straightforward, okay? When you're adding the vectors, so the reason I say be careful is because if I were to have said instead at the end that I have this is 1 kilogram traveling at this in this direction with a speed like 2v, for example, and then asked to work out v, I would have to say that this is a positive velocity, so I would say that's 2v minus 2v, right? So I'd end up, if v is the same, I end up with 0 momentum. Obviously that's not the case for this, but this was just an example. I'd have to minus the things that go in the opposite direction. Okay, now let's have example 2, which is where I'm going to introduce a force. So let's say that I have a ball, and this is a bouncy ball, so it weighs, I don't know, let's say 500 grams. It's a pretty heavy bouncy ball. So this is 0.5 kilograms, and I'm throwing it at the wall, and it initially moves with a velocity of 10 meters per second. And this wall is a fixed position, so nothing really moves this wall. So what actually happens is the ball will then bounce back with the same mass and the same velocity, so 10 meters per second, but it's now 0.5 kilograms. And what the question will ask is what force is exerted on the ball when the contact time, so the amount of time that the ball was actually in contact with the wall, is 0.3 seconds. Okay, now this involves, as soon as you see this phrase contact time, or you get anything involving momentum and time, you automatically want to go to this equation. Okay, so what we can say is our change in momentum is going to be our final momentum minus our initial momentum. I'm going to define this direction to be positive because now I've got things moving in two directions. My final momentum is this second one here. So my final momentum is actually minus 10 times 0.5, which is minus 5. And my initial momentum, so it's final minus initial, so now I have to minus my initial momentum, which was also 5 but positive, divided by 0.3. So this is equal to minus 10 divided by 0.3, which will give you a force of minus 33.3 recurring newtons. Okay, now again, be careful with this phrase here, exerted on the ball. Make sure your force does make sense in the direction that the force is going. So the force is pushing it in the negative direction, which makes sense. We could also then say what force is exerted on the wall by the ball, and that would just be, so that means that the force exerted on the wall is just going to be the positive of that, because with Newton's laws, it has to be equal and opposite. So it's the same magnitude in the opposite direction, so the positive direction. Okay, so this is everything that you'll need to know for momentum. I would say make up practice questions, give yourself some situations where balls are bouncing or joining together or bouncing off a wall or something like that, and then just apply your formulas and then see how much you can investigate and do loads of practice questions. Thank you for watching.